All right, good morning. My name is Jonathan. This is Zhenpeng. We're PhD students here in the BU NIS Lab, and this morning we'd like to give a quick overview of some research that we've been doing related to strategic management in shared cloud services. So in a cloud market, you can have multiple different choices. The more traditional model would be purchasing resources from a single provider who's provisioning them, which of course is how the Googles and the Amazons of the world work. But you might also, say, be deploying OpenShift in an internal environment and then charge your users using the same model so that way they prevent the users from trying to oversubscribe and overwhelm the system by trying to claim all the resources for themselves. But in, say, between providers, you might have an open exchange model with an auction where providers or users who have spare capacity can then offer up resources, and then those who want the spare resources can then bid on them. But regardless of how your market is set up, what you ultimately have here is an interplay between engineering and management decisions, because you need to basically decide how you want things to work, and in particular, you want to prevent users from gaming the marketplace and distorting it so that way they benefit at the expense of everyone else. But in order to be able to set up a system to prevent that, we need to first understand how the users make the purchasing decisions in the first place. And we explore this through game theory.
Okay, so in the settings of game theory, we have the players, which could be the cloud users, and the potential providers. The providers could be the providers, a separate provider that operate the cloud, or the users themselves in the marketplace. So we want to reason about the strategies of these players. We want to find the best response against other players' actions. And what we are looking for eventually is an equilibrium, which is a state that no player wants to deviate from it. In other words, that each player is playing its own best response. So what's next after we know the existence of this equilibrium? We can characterize it from and understand the system from multiple aspects. For example, is this equilibrium unique? Is it stable? And from the provider's perspective, we can reason about the provider's revenue at a given equilibrium. And from the we can also look into the system social welfare, which is defined as utilities. The sum of the utilities of both the providers and the users. And in many cases, we may find that the social welfare is not optimal because the players in a game will assume that they are selfish, and so that may be a problem. So one key insight from our research is that it is possible to increase the revenue from the provider's perspective or the social welfare from the society's perspective, even if we do not invest in additional resources. And how are we able to do that? We can achieve that goal by judicious pricing and resource allocation, so that we can get the users to behave what we expect them to do, even if they only care about their own utilities. So next, we want to go a little deeper into our work and show what we found. The first one we want to talk about is the analysis of these shared buying computing systems. So in such a system, basically you have the shared users, which are like the free tier users of the cloud, and you have the buying users who own some computing nodes. And the decision in such a system is that we like the idle resources of these buying users to be accessible to all of the other users. So in such a form of sharing, the utilization of this system resources is enhanced, and everyone gets better off. So one takeaway from our analysis is that heavy users with large amount of workloads are in some sense subsidizing the light users, which seems not fair and may lead to the possible emergence of this free riders problem, which means that the heavy users may may split their workloads and join the system as multiple light users without paying too much. A typical example of this shared bank computing system is the shared computing cluster at BU, which is located at MGH-PCC. So from this figure on the left, you can see how the ICC is widely used by the BU community. And the data from ICC shows that this kind of sharing did enhance the utilization of the system. However, it is still not social optimal. So this figure on the right shows the number of the buy-in nodes owned by a product versus its total workload. And you can see that there are a lot of outliers which do not behave as what we expect them to do, and so which means that they are not incentivized well enough in such a system. So next question is there a better solution in terms of the social welfare? So for example, in the open cloud exchange model, we can consider implementing a decentralized marketplace in which we let the users themselves to allocate their resources through an auction mechanism, which could be a more efficient way of sharing if designed properly.
All right, so another thing we looked at is incorporating advanced reservation plus preemption into a system. So in this model that we looked at, we have the ability to basically be like a just-in-time user, like I need resources now, I will try and purchase them. But you might also be like, okay, well, I know I have a need for a large amount of resources 3 weeks from now when I run my experiment. I would like to be able to get a better chance of securing them. And so we allow them to get, or rather purchase an advanced reservation, and they would get priority over those just-in-time users. So we compared this to a system where there's no preemption whatsoever. Like you can still purchase at priority, but if once you're in service, you can't be kicked out. And a strict priority preemption where you purchase priority, but anyone with higher priority can kick you out even if you have a reservation. Under our model, if you have a reservation, once you're in service, you can't be kicked out. If you don't have a reservation, then you can be. But even if you aren't able to get in when you wanted, you still have priority over everyone who tried to make a reservation after you did. And we find that in comparing these models, the advanced reservation plus the preemption maximizes the revenue, as shown in this plot, where the green is the model that we studied, and then the blue is the no preemption whatsoever. And so, of course, the answer, or rather the question we want to ask is why? Well, the answer seems somewhat obvious. Users have incentive to avoid latency. Actually, the novel thing about this work is that under the model that we studied, the more people who make a reservation, the greater the incentive is for other people to do so, and that actually drives the cost customers are willing to pay higher. Whereas in the other models, the more people who do so, the less likely people who show up later will want to, because they're more likely to get preempted anyway, and so they're willing to pay a lower cost. But here, because purchasing allows users to avoid latency, they're willing to pay even more. And so one thing that we want to look at now then is, given what we know about this customer behavior, if we move towards a more auction-like system, if we permit advanced bids and give those priority over someone who tries to basically a just-in-time bid, how does that impact user behavior, and what mechanisms would need to be put in place in order to ensure that the mechanism isn't abused by someone who is trying to, say, hog all the resources, so I'm going to bid indefinitely into the future for everything that's available in order to get priority. So in summary, through game theory, we can understand these trends of user behavior in clouds. We can identify potential improvements through policy, and our future work includes applying these results to other market setups in order to see how those lessons translate and what else we can do to ensure the best benefit to all users. Thank you.